Today we are going to be looking at our second unit or second lesson from our polygons unit. Today we're going to look at polygon symmetry. So hopefully you remember a little bit about symmetry from middle school as well. We're going to talk about a different kind that you probably haven't discussed before, but one of the symmetries should be familiar to you. First of all, what is symmetry? When two or more parts are identical after a flip, a slide, or a turn. Most of you have thought about reflection symmetry. This has to do with a flip or a line straight down your shape where one side will be a mirror of the other, kind of like the picture of the dog here, where the left side and the right side appear to be mirror images of one another. But there is also rotational symmetry and point symmetry. So today we're going to look at symmetry in lines of symmetry in regular polygons, as well as rotational symmetry. So I'm going to have you take a moment and watch this video with me. She does a pretty nice job.
Writing's not that easy, but Grammarly can help.
We have to wait for the ad, I guess.
This sentence is grammatically correct, but it's wordy. Lines of symmetry in regular polygons. A regular polygon is a polygon with equal sides and equal angles. Let's take a square as an example of a regular polygon. As we learned before, the square is a symmetrical shape. It has one vertical, one horizontal, and two diagonal lines of symmetry. But what about other regular polygons? How many lines of symmetry do they have? Let's figure it out together. This triangle is a regular polygon. All of its sides are equal, as well as its angles. This type of triangle is called equilateral triangle. Now, can you tell if this triangle is a symmetrical shape or not? Well, we can split it into two identical halves across this vertical line of symmetry. Are there any other lines of symmetry in this triangle? Notice that we can fold our triangle like this to get two identical parts. And we can fold it this way too. What if we tried to fold it horizontally like this? As you can see, the resulting parts are not identical. So, an equilateral triangle has three lines of symmetry, one vertical and two diagonal. What about regular pentagons? In a regular pentagon, we can find one vertical line of symmetry. And as you can see, four diagonal lines of symmetry, which makes them 5 lines of symmetry in total. While this regular hexagon has 6 lines of symmetry, the first one is vertical, and the second one is horizontal, while the other 4 lines of symmetry are diagonal ones. This regular octagon has 8 lines of symmetry, one vertical line, one horizontal line, and 6 diagonal lines of symmetry. To summarize, let us have another look at the polygons and the lines of symmetry in each of them. In this lesson, you learned how to identify lines of symmetry in regular polygons.
Okay, so that video took us through some of the things maybe that you had talked about in previous lessons, previous years, about that line of symmetry, the folding in half that's occurring. But all of those were in regular polygons, which is where our focus is going to stay today. So, did you notice, I hope, that the pattern existed for the number of lines of symmetry within those regular polygons? The triangle had 3 lines of symmetry. A square would have 4 lines of symmetry. The pentagon had 5. The hexagon has 6. Hopefully you're catching on to that. The number of sides of the shape is equal to the number of lines of symmetry. Beyond that, there's even more of a pattern. So if the regular polygon has an even number of sides, 4, 6, 8, 10, 12, and so on, then the lines of symmetry will actually be drawn in 2 different ways. Some of them, half of the lines, will be from a vertex to a vertex. That's what this one is here on the left, a vertex to a vertex. The other half of them will be a midpoint to a midpoint. So from the middle of a side to the middle of another side. If your regular polygon has an odd number of sides, so 3, 5, 7, 9, 11, 13, and so on, then all of the lines, every one of them, will be a line of symmetry that goes from a vertex to the midpoint of the opposite side. So I did a little pentagon here, and you can see we have the midpoint of this side, and it connects then to the opposite vertex. So all of those are going to be vertex midpoint. So you've got in an even number of sides, vertex, vertex, midpoint, midpoint. In the odd, vertex to midpoint. So then I want to talk about rotational symmetry. And yes, I know that was a lot coming at your screen all at once. So just look up at the words with me for a moment and ignore all those green diagrams. A figure has rotational symmetry if it can be rotated by an angle between 0 degrees and 360 degrees so that the image coincides with the pre-image. Okay, now that's kind of wordy. So in other words, if you turn the figure, it will fall directly on top of itself at some point, or maybe several points, during the course of that turn. So I had a website where I could play with something and show it at each of these different angle measures, and I could go all the way around the whole 360. So I just picked some to stop at. So here it was at the original. This point is the point that I was rotating, that red one. Okay, this is at 0 degrees, the way it originally stood. So I started taking that red point, which was right here in that yellow that's behind there, that's the original. And I started just turning it. And I was turning to the left, okay? So I turned it 44 degrees, and then I kept turning, and I got to 62 degrees, and I was almost right on top of that next vertex, but I wasn't quite there. So I kept turning, and at 72 degrees, the green shape is exactly over top of the yellow, which remember back here, the yellow was representing the original shape. So it's right on top of the original shape. It's right on top of itself. So 72 degrees is an angle of rotational symmetry because it falls right on top of itself. So then I kept turning. So I went from here, kept turning to the left. Here's 118. You'll see the green is not on top of the yellow. I kept turning, and at 144 degrees, I'm sorry, that thing at the bottom is down there. At 144 degrees, it was right on top of itself. And I kept turning, and it ended up happening 5 times. So at 72 degrees was when it was at the first vertex. 144 degrees was the next one, then 216, then 288, and then of course, all the way back at 360, it should fall back on top of itself. So here's what I want you to notice about those measures. If I look down here, the first one is 72 degrees. But if I take that and add that same 72 to it, I get 144, which was the next one. And if I add another 72, I get 216. And if I add another 72, I get 288. And if I add another 72, I get 360. So if I can find this number right here, the original first rotational angle, it will allow me to find all of the others because I can just keep adding that number over and over and over again. But the key is I have to find that first one so that I can figure out all of the angles at which point the turn is going to cause it to stop right on top of itself. Well, luckily, it is actually pretty easy to find that degree of rotational symmetry. Because a full rotation is 360 degrees, we're going to take that 360 and we're going to divide it by the number of sides the regular polygon has, because the polygon has the same number of sides as it does angles. So if we divide by the sides, we're really dividing by how many angles there are as well. A pentagon has 5 sides. So 360 divided by 5 is 72. And that's what we kept adding every time in order to get to our 360 degrees in the end. So let's try it again. What are the angles of rotational symmetry for a regular octagon? Since a full rotation is 360, we're going to take 360, divide it by the number of sides in the regular polygon. An octagon has 8 sides. So 360 divided by 8 is 45 degrees. So the first rotational symmetry occurs at 45 degrees. Then we're going to keep adding 45 and keep adding it and keep adding it until we get to 360. So follow along this line here. We start at 45, the answer we got when we divided, and we just keep adding that number. So 45 plus 45 is 90, plus another 45 is 135, plus another 45 is 180, plus another 45 is 225, plus another 45 is 270, plus another 45 is 315. 315 plus another 45 is 360, and that's when we stop, when we end up at the answer of 360. So every one of those answers, 45, 90, 135, 180, 225, 270, 315, and 360, are all the angles of rotational symmetry for a regular octagon. Notice there are 8 angles of rotational symmetry. There should be the same number of angles of rotational symmetry as there are number of sides in your figure. So your lines of symmetry should be the same as the number of sides, and your rotational symmetry angles should be the same as the number of sides. Are you catching that pattern, I hope? Okay, so today on your assignment, you're going to be looking at lines of symmetry. How many of them are there? And then also looking at rotational symmetry, how many of those are there? And dividing out to figure out what all of those angles are. So dividing by the number of sides and then adding that number over and over again. As always, if you have any questions, please don't hesitate to let me know that you have something that you want me to go over with you. I'm happy to do that.